Hey, this is JuanTutors, and today we are working on the August 2025 Geometry Regents. This whole video is vertical so that we could fit more writing in the space. So we are basically going to get started right away, except for the one big piece of advice that I give students all at the beginning. I sometimes go through a big rundown of the front page so that you don't have to read it later. But the biggest piece, the biggest, most important thing to read in this page is this. Note that diagrams are not necessarily drawn to scale. A lot of teachers will tell you, well, that means that you can't assume that they're drawn to scale. And I just want to be clear with you. That's technically true. Technically true. However, if you think about it, when you're taught geometry, if every single diagram that you were ever shown was not drawn to scale, wouldn't it be insanely difficult to understand geometry? I think so. And the Regents people also agree. So what that means is that all diagrams are not, we could cross out the words not necessarily and write almost definitely. And I have my students cross that out and then write that in whenever they're doing practice Regents. And they say it in this test, I think 5 times. And we're going to get started. The very first chance they get, once again, not necessarily drawn to scale. We're going to cross out the words not necessarily, and we're going to write almost definitely. And with that, we are going to get started with number 1. An equilateral triangle is continuously rotated around one of its altitudes. The three-dimensional object formed is a cone, sphere, cylinder, or pyramid. Okay, so before I even get an answer to this, I know that the rotating a two-dimensional figure in three-dimensional space is going to produce circular objects. So a pyramid doesn't have circular edges. So the pyramid has to be wrong just from moment 1. So now let's look at what's being rotated. It's an equilateral triangle, and it's rotated around one of its altitudes. Okay? That's not the best equilateral triangle I've ever drawn, so let's try that again. Okay. Let's see if, yep, nice. So it does edit that. I love this software because it edits those shapes for me. Now, if we rotate over one of its central line, right? So let me see if I can move that over just a little bit. Nah, it doesn't work. Okay, so when we rotate this, another way that I like to think about it, if I'm teaching my students, I literally bring a drill bit and a drill in, and I spin the object so that they could see what it looks like in 3 dimensions. But if you imagine putting that on a pencil and kind of spinning it like this, what shape does that make? The shape that it makes, the bottom makes a circle. And in fact, all the points on the edge make a circle. So what shape is this? This is a cone. So this is the shape that this makes. I'm going to do my best to, do some process of elimination in this one, but I've done so many videos in the past that focus so strongly on process of elimination that that's not going to be my main target. My main target is going to be how to do problems in the positive sense. What that means is I'm going to focus on how you get the answer to the questions from mathematical principles, but I will insert some process of elimination because some of the problems can be done without even doing much of the actual math that they want us to do. On that note, number 2 says that on the set of axes below, quadrilateral BDGF, in that order, BDGF, is rotated 90 degrees clockwise about its origin and then reflected over the y-axis, so clockwise, and then reflected over the y-axis. The image of quadrilateral BDGF is quadrilateral MQSP, in that order. Side BD will always map onto MPPS, MQSQ. And in this case, what really matters is the order of the vertices. So when they write this, they are required to give the order of the vertices in the order that they correspond to each other. So MQSP, QSP corresponds to shape BDGF in that order. BDGF. So when they say segment BD, which one does that correspond to? It does have to correspond to MQ. With that, we go to number 3. In right triangle JOE, hypotenuse JO equals 31.8, and the measure of angle J equals 38 degrees. To the nearest tenth, the length of EJ is 19.6, 25.1, 40.4, or 51.7. Now, before, again, I even do the math, they did say that the hypotenuse is 31.8. The hypotenuse is the longest side of a right triangle. Therefore, the legs have to be shorter than 31.8, so that already crosses out 2, and we have a passing problem. What is a passing problem? A passing problem is a problem that we've eliminated 2 of the answers. And the reason that we call it a passing problem is that if you look at the scoring table, the conversion chart rather, if we look at what is required to get a 65, 34 points is required to get a 65. Now that is more than half the multiple choice questions, which is a notification for teachers who say focus only on the multiple choice. It's not complete enough advice, and I'll explain why as I go on. But this is 17 multiple choice questions. About half of them is 12. But if you get a few points out of the part 2s, 3s, and 4s, then you really only do need about half the multiple choice, which means that if you eliminate half the choices in every multiple choice, that statistically doesn't lower nor raise your grade relative to a passing grade. That said, in this problem, they said that hypotenuse JO is 31.8. There we go. Nice. Okay, 31.8. 31.8. And the measure of angle J is 38 degrees, slightly less than 45 degrees. So I'm going to put J up here. Okay? So 38 degrees. 38 degrees. That makes this angle 90. 90 minus 38, which is equal to 52. 52. Okay? So given that 52, we could actually say that this is O, this is E now. We could say that the altitude going vertically is the longer edge, the longer leg of the right triangle, and that so JE is the longer leg, and EO is the shorter leg of this right triangle, which makes 25 a really nice, favorable answer. But we don't know if that's what it is. But 19.6 is still more than half of 31.8. So we do have to do some good math to figure out what it is. So we notice, given the 38 degree angle, let's work with the 38 degree angle. This is the adjacent leg, and this is the hypotenuse. And we remember SOHCAHTOA. And the one that has the adjacent leg and the hypotenuse is this one. So cos of J is equal to the adjacent leg divided by the hypotenuse, so that cos of 38 equals, EJ, over the hypotenuse, 31.8. Let's go to over here so we have a little bit more space to write. So we had, again, cos 38 is equal to EJ over 31.8. And to get to solve for EJ, we could multiply by 31.8. If you want to cross multiply, you could do that too, but I'm going to multiply by 31.8. And I get that EJ is equal to that number, 31.8 times cos 38. And at this point, we then have to go to a calculator and we make sure we're in the degree mode. Okay, degree mode, enter. So I pressed mode and then went down to degree mode and made sure that degree is highlighted. Quit. Now 31.8 times cosine of 38, and that's equal to 25.05. 25.05, which is around 25.1, according to the answer choices. They said to the nearest tenth, 25.1. Okay? So far we're doing great. So far we're doing great. Let's hop right over to number 4 with a hemisphere. A lot of students get this one wrong by not considering a hemisphere, but they actually consider a sphere. In other words, they go through the process of getting the volume of a sphere and then they stop. Other students get this wrong because they don't even think to say, oh, a hemisphere is half of a sphere. So if I just get the volume of a sphere and cut it in half, then I got that volume of the hemisphere. So that's what I'm going to do. I'm going to get the volume of the sphere and well, let's read the problem. Number 4, a hemisphere below has a radius of 8 centimeters. And I see that that's true, drawn to scale for sure. To the nearest cubic centimeter, the volume of the hemisphere is 201, 268, 1072, or 2145. Now, for me, I like doing process of elimination if it's quick for me. And if I put this hemisphere in the smallest gift box that I can, that gift box would be 16 by 16 by 8. And 16 times 16 is 256. That multiplied by 8 is about 2048. Okay, it is 2048. But that eliminates 4 because now we have a box of volume 2048 that contains this volume completely. However, the hemisphere takes up about half the box's volume. In other words, I could still it's got a lot of edges on the top, not many edges on the bottom, but it still takes up about, I would say, maybe half the volume, maybe a little more, a little bit less. So this answer is looking mighty fine. And these answers are looking too small to me just based on my estimate of a 16 by 16 by 8 box. Now, let me address how I crossed things out. Notice that I crossed things out at the number 4, but I crossed out choice 1 and 2 next to the numbers. The reason I crossed out number 4 at the number is because I'm 100% sure number 4 is not correct. The reason I put an X next to number 1 and number 2 is that next to it, not on number 1 and number 2, next to it is that I suspect that it's wrong. And the reason I put a checkbox next to number 3 is that I suspect that it's correct. Or it has something that allows it to be possibly correct, potentially correct. How do I mark when I am sure that it's right? I circle it. And so I cross it out. I cross the number out if I know it's wrong. I put an X next to it if I suspect it's wrong. I put a checkbox if I think it's right. And I circle the answer if I know that it's right. So how do I get this problem? The volume of this shape. I got the volume of a sphere. Now you might wonder, do I have to memorize the volume of a sphere? And that's a valid question. Let's actually go to the Regents. And let's go to the end of the Regents and let's see what formulas they give. So they do give some volumes, including the volume of a cylinder, a general prism, a sphere, a cone, and a pyramid. This is the full formula sheet. The formula sheet has shrunk a significant amount since the last time they gave the test, hasn't it? Only some volume formulas. That said, the volume of a sphere formula is right here, 4/3 pi r cubed. So we do not have to memorize that. We have it. They're giving it to us, so we're going to use it. Ideally, of course, you memorize it because there's a lot of things you do kind of have to memorize. But if you don't, oh well. 4/3 pi r cubed, which is equal to 4/3 pi times 8 cubed. And I could actually get this on the calculator. And that's what I am going to do. 4/3 times pi is above the exponent button, times r cubed, 8 cubed. And now remember, this is the volume of the sphere. So 2144.66, 2144.660585. I actually recommend putting all those digits into the paper. Now the volume of the hemisphere, how do we get that? Is equal to the volume of the sphere divided by 2, and that's equal to, according to my calculator, that answer divided by 2. 1072.33 0292, which according to my reading is the one that I suspected to be the answer, which is nice. Number 5, in parallelogram ABCD, diagonals AC and BD intersect at E. Which information is sufficient to prove that ABCD is a rhombus? Is it that AE is congruent to EC, or AC is congruent to BD, or AB is perpendicular to BC, or AC is perpendicular to BD? Now, the way I do this problem, I actually draw two things in this shape. I draw a parallelogram, which is definitely a parallelogram, but not a rhombus. And then I draw a rhombus. So I'm going to see, let's see if the software draws this parallelogram for me. Nice. And then I'm going to draw the best rhombus that I can. Okay. Let's see if I can adjust it with my mouse to make it a little bit more rhombusy. There we go. Rhombus is like more diamond-like, meaning, so like if you remember what you called a diamond shape when you were like in elementary school, it's diamond shaped. So all four sides are congruent. Okay, so and then we're gonna draw the label A, B, C, D. A, B, C, D. Now this one we're also gonna label it A, B, C, D, even though it's a totally different shape, because one of them is a representation of a parallelogram that's not a rhombus, and the other one is a representation of a parallelogram that is a rhombus. A, B, C, D. And this is the most general rhombus that we can draw. And now I want to draw the diagonals. Let's draw these diagonals. Let's see if it'll let me draw this diagonal nicely. Good. And then this diagonal nicely. Good. And then this diagonal nicely. And then this diagonal nicely. They intersect at E, so we got to label that too. E and E. Now that we have the diagrams labeled, let's look at these. Choice 1, AE is congruent to EC. That's this congruent to this. Now, this is already true for all parallelograms. Diagonals bisect each other, so this is already true. True for all parallelograms. Okay? Which means that it can't force the parallelogram to be a rhombus. So that's not it. Choice 2, AC is congruent to BD. Now, it could be that AC is congruent to BD, but what that does, if AC is congruent to BD, is that it makes it into a rectangle. See, a rectangle, if you draw the diagonals, that one's not going to straighten, but this is just a rough drawing anyway. So the diagonals are congruent, okay? So, I mean, okay. So the diagonals are congruent, so this makes it a rectangle. Choice 3, AB is perpendicular to BC. This also makes it a rectangle. Because all that a rectangle is a parallelogram with 4 right angles. So, and in fact, you could even say a parallelogram with 1 right angle, because if it's a parallelogram with 1 right angle, then all 4 angles are right angles. And that only leaves choice 4, that AC is perpendicular to BD. And that, in fact, is enough to show that the parallelogram is, in fact, a rhombus. Because if these are perpendicular, then all 4 angles are perpendicular. And then you could do clever things like side angle side to prove that any 2 of the 4 small triangles are congruent. So, for example, this is congruent to itself, and then this length is congruent to this length. This angle is congruent to this angle. So by side angle side, triangle DCE is congruent to triangle BCE. And by corresponding parts of similar triangles are congruent, by CPCTC, corresponding parts of congruent triangles are congruent. This line segment is congruent to this line segment. AB is already congruent to DC, and AD is already congruent to BC. So that's a rhombus. Ooh, that was interesting. I don't know what happened there. Let's hop over to number 6. Trapezoid Josh, Josh, shown below, has non-parallel sides JH, and OS. So it is a proper trapezoid, not a parallelogram. And the measure of angle J is 65 degrees. It sure looks like it's 65 degrees. The measure of angle O is 30 degrees. Sure, that looks like a 30-degree angle. The measure of angle OSA is 80 degrees. That does look like an 80-degree angle. And the measure of angle SHU is 60 degrees. 1, 2, 3. So they want to know the measure of angle HSA. Okay? HSA. And I like, actually, since I mark it with dashes, if I have a fourth angle to mark, I just convert the dashes to Roman numerals. So I mark this one as like IV. Meaning Roman numeral 4. So they want to know the measure of angle HSA. This is the first really good problem. Let me see if I had other diagrams above. I did have another diagram above. You could use scale there. But this is the first really good diagram that I got to get to really establish that advice that I gave you about assuming or not assuming that a diagram is drawn to scale. It's true, if you're aiming for like 100 on this Regents, you shouldn't necessarily assume that the diagram's not drawn to scale. However, if you're stuck, this is really good advice for you as a 100 seeker, but it's also very good advice for those who are just seeking to pass this Regents. Scale can be used if we assume that if this diagram is drawn to scale without any reason to assume it. We're going to get reason to assume it in a second, and that's actually the big important thing. But if we assume that this diagram is drawn to scale because we just really struggle and don't even know how to check anything, then I'm going to say that angle HSA looks like that 80-degree angle, maybe a little bit smaller. So I would say that 70 and 65 degrees are looking mighty fine. 60 degrees is looks smaller than that angle, and the 65-degree angle actually also looks smaller than that angle. So 70 degrees is looking fine to me, only based on scale. Only based on scale. And that's assuming it's drawn to scale. Now, let's actually establish whether it is drawn to scale. When I was reading it, I had mentioned the 65-degree angle does look like a 65-degree angle. The 60-degree angle does look like a 60-degree angle. The 80-degree angle does look like an 80-degree angle. And the 30-degree angle does look like a 30-degree angle. No other part of this shape violates any of that information. So this diagram up to the angle measures is definitely drawn to scale. So now that we've actually confirmed that it's drawn to scale, we can actually state that 70 is the most likely correct answer without actually doing the math. We just looked at it and said it looks like a 70-degree angle. So how do we actually do this problem? It's a little bit of angle chasing. I noticed I was working with a student this past week, and she had mentioned that this one is one of the problems that is a struggle for her. So what I would say to her is this: you look at a part of the shape and remember what you know about that part of the shape. For example, OSA is a triangle, and remember everything that you know about triangles. We have an 80-degree angle and a 30-degree angle. So the measure of angle SAO would be the measure of angle SAO is equal to the measure is 180 minus the measure of angle ASO 80 minus the measure of angle SOA 30, which is equal to 70 degrees. So 70 degrees. Okay? And in fact, now if I look at angle, there are other ways to do this problem. I'm going to use alternate interior angles are congruent when you have two parallel lines. Remember that this line and this line are parallel. This line and this line are parallel. So I'm going to use alternate interior angles. But it turns out in this one, you could actually do more angle chasing to get the answer. That's okay. So this is a 70-degree angle. So that up here, angle HSA, which is the angle that we seek, has to be congruent to angle SAO, because alternate interior angles are congruent. so that, again, angle HSA is congruent to angle SAO. So they have the same measure, 70 degrees, which is exactly what we had suspected. Scale. It's a beauteous thing. This is another one that you could use scale. Well, the first thing I'll say when you're taking the test, some students don't bother labeling. Probably not a good thing to not bother doing, right? So you should definitely label everything that you can. So this one says in triangle ABC below, ABC, that's a triangle, points D and E are on AB and CB, AB and CB respectively, such that DE is parallel to AC. Now they told us that this and this are parallel. They sure do look parallel. Great. Now if AD is equal to 8, so that's from there to there. Okay. If DB equals 4, that's from D to B. Now DE is equal to 6, then what's the length of AC? Now this is one where I would use scale. Everything that they said looks about right. DE does look parallel to AC. The length that's 8 does look like it's double the length of 4, and the length of 6 looks like a length in between 4 and 8. This diagram is drawn to scale. So if I use scale, I think that AC is quite a bit more than double DE, but it's not 4 times as big. 4 times as big would be like, well, DE to that point and then double that again. Ooh. I mean, do I have enough space to draw that dot? Let me see. That would be like that. Call this E prime and then E double prime or something like that. That line segment AC is not quite that long, but if I draw a dot in between, that's 18. So like if you do 6, 6, and 6, that looks like the length of AC. So 18 is looking mighty, mighty, mighty fine. But let's actually do this problem via the good old methods that we've learned about these triangles. Triangle BDE is actually going to be similar to triangle BAC. How can we prove it? Well, in triangle BDE, we have this angle here. Let me use a different color here. We have this angle here and this angle here. And those are corresponding angles with 2 parallel lines cut by a transversal. Corresponding angles are congruent. So these are congruent. Similarly, angle B is congruent to itself. Put an X there just to say that it's congruent to itself. And angle B is an angle of triangle BDE and triangle BAC. So these 2 triangles have 2 congruent pairs of angles, so they're similar. Triangle BDE is similar to triangle BAC. BDE is similar to BAC, okay? And with corresponding sides in that order. So BD over BA is equal to DE. So that's the first and second vertex over the first and second vertex is equal to DE, second and third vertex, over the second and third vertex AC. And then I can plug in some numbers here. Let's see. I got 4 over BA, careful, 12, is equal to DE, 6, over the unknown length of AC. I can, however, it's one unknown in one equation. I can cross multiply to get AC. And I get that 4 AC is equal to 12 times 6. I could multiply that now, or I could divide by 4 first. And I got that AC is equal to, according to my calculator, I do plug it into my calculator, I get 18. Okay? Which is exactly what I had suspected. Number 8. Nice circle equation. This is one of the fundamental topics that you really kind of have to know and memorize. And another piece of this problem, square roots, you got to remember that r squared is in the equation, not r. So the radius is the r squared. So on the set of axes below, circle C has a center with coordinates 2, -1. Sure does look like 2, -1. When they graph, they actually have to graph accurately. Forget about just drawn to scale. Graphs have to be drawn accurately. In other words, This diagram need not be drawn to scale, although we just found out that every diagram so far is drawn to scale. But graphs are absolutely required to be drawn to scale because the graph paper exists. And the things that are on the graph paper have to mean what the graph paper says. So things have to be drawn to scale. So on the graph paper, so 2, -1, and in fact, does look like that. Then, which equation represents circle C? Is it x minus 2 squared plus y plus 1 squared equals 25? Or x minus 2 squared plus y plus 1 squared equals 16? Or x plus 2 squared plus y minus 1 squared equals 25? Or x plus 2 squared plus y minus 1 squared equals 16? So there is one that I can eliminate, or there's two that I can eliminate pretty quickly. If I count up, 1, 2, 3, 4, 5, r is equal to 5. And r squared equals 25. So any of these that imply that the radius is anything other than 5 has to be wrong. So choice 4 and choice 2 are wrong, and we already have a passing problem. So now what is the piece of information that you have to know for the purposes of this problem? So given a circle with center HK and radius R, okay, that implies that x, I'm going to write this in a different color so that's easily seen. That implies that x minus h squared plus y minus k squared equals r squared. Okay, so notice that h and k are being subtracted from x and y. So h is equal to 2 and k is equal to -1. So the equation has to be x minus 2 squared plus y minus -1 squared equals r, which is equal to 5 squared. And which one matches this? This one matches here, this one matches here, and the y minus -1 is equivalent to y plus 1 squared. So that one also matches here. Okay, so everything in the equation in choice 1 matches exactly. Number 9, on a set of axes below, triangle D prime E prime F prime is the image of triangle DEF. A transformation that maps DEF onto D prime E prime F prime is a reflection over the line y equals x, or a reflection over the line y equals -x, or a point reflection through the origin, which is equivalent to a rotation by 180, or a translation 4 units left and 4 units down. Okay, so let's see which one of these can we verify that don't work. If I translate DEF 4 units left and 4 units down, D gets transported to D prime, but E gets transported to some random place up here, not down here. So a translation is not going to do it. A translation doesn't only preserve congruence, but it preserves parallelism. So as a result, physically in space, when you slide an object left, right, up, down, however you want, translate it, E would be the top vertex, so E prime under a translation would be the top vertex, but in fact D prime is the top. Another one that I could eliminate pretty quickly, the reflection over the line y equals x. Reflection over the line y equals x keeps the triangle in the first quadrant. So that's going to be definitely not it. So I can eliminate that real quick. How about a reflection over the line y equals -x? That one's not quite as obvious, but we could do the math. Let's see. We could do the math here. Now a reflection over the line y equals x to y equals -x does reflect to -2. So it does reflect D to D prime. But what it does to E is 1, 2, 3, 4, and 1, 2, 3, 4. It reflects E to here, E prime. And then here, F, 1, 2, 3, 4, 5 to 1, 2, 3, 4, 5. Reflects F to F prime here. And that's clearly not the same shape, right? So it's not a reflection over the line y equals x. So we're gonna cross that one out, and it really does leave only one more. And so now, how about a point reflection through the origin, which is an equivalent to a 180-degree rotation. Let's call it counterclockwise rotation. It turns out 180 counterclockwise and 180 clockwise are the same transformation, but it's also equivalent to 90 degrees counterclockwise rotation twice if you need to follow some math. And the other thing that it does is that it negates all coordinates. Okay? So I should say a 180-degree rotation over the origin. Or over or around the origin. Okay? Okay, so anyway, 180-degree rotation or a reflection over the origin negates the coordinates. So we have 2, 2. And the coordinates of D prime would be -2, -2, which is in fact correct. F has coordinates, let's see, 7, 3. And so F prime would have coordinates -7, 3. -7, -3, which it does. And then E has coordinates 5, 3. Nope, 3, 5. Made a common student error right there. 3, 5. And so E prime would have coordinates -3, -5, which in fact it does. So the answer is a point reflection through the origin. Number 10, in circle O below, secants PCA and PDB are drawn from external points P. If PA is 17, PD is 10, BD is 12, what is the length of PC to the nearest 10th? Is it 7.1, 7.7, 12.9, or 14.2? Now, this is yet another one that using the scale is a useful thing. The lengths that, the 10 does look ever so slightly shorter than the 12. The 17 looks longer than the 12. The PB being 22 looks longer than the 17. So this diagram is drawn to scale. The circle looks like a circle with the center looks like it's placed about where the center would be. So this diagram is drawn to scale. So if I turn the page maybe, or if I compare, PC looks like it's a little bit longer than PD. So I suspect that one of these two answers is good, with this one looking better for me and these not looking so good. Okay, that said, so it's looking like PC is greater than PD. Now, is that actually true? There is math that says it, if you happen to know how the ratios work. If one secant is shorter than the other, then the outer part of the shorter secant is longer than the outer part of the other secant, and then the interior part of the shorter secant is shorter than the interior part of the longer secant. But that's if you happen to know that. A better way to do it is to actually go to the formula, and there is a formula. It's a product formula. So the product formula says this, that the outer part of secant 1, okay, times the whole part, the whole of secant 1 is equal to the outer part of secant 2 divided by the whole part of secant 2. Okay, so in this case, if we actually plug into this formula, we actually get that for secant PCA, the outer part is PC multiplied by the whole secant PCA, so 17, and that's equal to the outer part of secant PDB, which is PD, which is 10, multiplied by the whole secant, 22. Again, this is PC, outer part of first secant, divided by, multiplied by the whole secant PA, is equal to the outer part of the second secant PD, multiplied by the whole secant PB. And now if we divide both sides by 17, we get our answer. And in fact, I could see that 10 is being multiplied by 22 over 17. So it is bigger than 10. And that does confirm that choice 1 and 2 are incorrect. But I do need to get my calculator out. It's going to block off the numbers a little bit. Let's see if I can move the numbers a little bit for a second. 10 times 22 divided by 17. And the calculator says 12.94. I didn't get the rest of those numbers. 94117647. And this is now notice I wrote all the digits and then I round. Then it sets to the nearest tenth, 12.9, which does do that. The reason I write all the digits is for muscle memory, for when I get to part 2s, 3s, and 4s, where writing all the digits is going to actually be beneficial. So that's why I write all the digits. Number 11, in the diagram below, CD is parallel to AB. Notice that I'm labeling as I'm reading, and CB bisects angle ABD. So that ABD has is cut into two congruent angles. And then which statement must be true? Is it that CD is congruent to AB? Or is it that AB is congruent to BD? Or is it that CDB is a right triangle? Or is it that CDB is an isosceles triangle? Some of these don't make sense. So here's the thing. A is completely free. So AB could be as long as, or short as they want to make it. So AB can't be said to be congruent to anything specific in the rest of the diagram. So AB can't, so choice 1 and choice 2 have to be incorrect. The third thing, the question about whether triangle CDB is a right angle or isosceles triangle, which are the only other two choices. Now, this is what we can say. Does AB look parallel to CD? Yeah, definitely is parallel to CD. Horizontal lines are parallel. Then those two angles that are said to be congruent, do they look 100% congruent? 100% they look congruent. So then we look at triangle. So this diagram's drawn to scale, minus some minor size changes that are allowed. Again, A is free to roam. That said, does it imply that the triangle CDB is a right triangle? Well, I could look at the triangle and I could see that it's not even drawn as a right triangle. So they're not trying to trick us here. And they're doing us a favor by drawing it as not a right triangle, because it doesn't look like a right triangle. It does look like an isosceles triangle. It does look like that. And if I didn't know how to do this problem, I would literally circle isosceles and walk away and get the points. So how do we do this problem though? Angle ABC. So remember that CD and AB are parallel, and they're cut by transversal CB. So alternate interior angles are congruent. I just wrote pi. Congruent. Okay? So that means that angle ABC is congruent to angle DCB. Those two angles that I just labeled. This angle and this angle that I just labeled are congruent. And this one was already congruent to this one. So triangle CDB has two congruent angles. Okay, so what does that imply? Well, That implies that it's isosceles. A triangle with two congruent sides is isosceles, and there is an isosceles triangle theorem which states that if the triangle has two congruent sides, so it's isosceles, then it has two congruent base angles. And then the converse of the isosceles triangle theorem says that if the triangle has two congruent base angles, then it has two congruent sides, and therefore is isosceles. So it in fact does prove that it's isosceles, but nothing makes angle D be forced to be a right angle. D is in fact free to vary as long as AB stays parallel to CD. So if you move point D down a little bit, down and maybe to the left, while you move A up, then you still maintain the properties of the shape. Okay, number 12, line H is represented by the equation y equals 2/3 x minus 4, which equation represents a line that is perpendicular to line H and passes through the point 6, 1. Is it y minus 1 equals 2/3 x minus 6, or y plus 1 equals 2/3 x plus 6, or y minus 1 equals negative 3/2 x minus 6, or y plus 1 equals negative 3/2 x plus 6? And a piece of advice, a lot of students that get to this problem struggle with this problem because there's two things that they're keeping track of. And they're trying to keep track of both things at the same time, when in fact, nothing is forcing them to keep both things in mind at the same time. And it's in fact better to keep one thing in mind at a time. For example, they said well, what I notice is that the coefficient is either 2/3 or negative 3/2. And I notice that we have a minus 1 and minus 6, or a plus 1 plus 6. So we have what I would call a 2-by-2 problem. And you can determine what the answer is by looking at the coefficient first, the slope first, and then looking at the subtraction and addition and see if they're matched. So the slope of the line H is equal to 2/3. The big important lesson that you need to know for this problem is that the slope of any parallel line is also going to be 2/3. And the slope of any perpendicular line is going to be the opposite reciprocal. So the opposite is the negative, and then the reciprocal 3/2. Since this said that the line is perpendicular to H, we know that the slope is going to be equal to negative 3/2. So that makes this one possibly valid and this one possibly valid, and it eliminates this one and this one. And so we have we have converted it into a passing problem, even if we don't know how to do the second part. The second part, though, goes back to exactly the circle problem. If it passes through a 0.61, so if it passes through, let's say h comma k, with slope m, then the equation in point slope form is y minus y1 is equal to I didn't use y1 in this because I used h. Y minus k is equal to m x minus h. I know that some teachers, actually almost all teachers, prefer x1 y1. I like hk, but if I used x1 y1, y minus y1 is equal to m x minus x1. But either way, based on this equation, we get y minus the y coordinate 1 is equal to the slope of the perpendicular line, negative 3/2, times x minus the x coordinate of the line of the point 6. And that does match exactly with choice 3. Number 13, I wonder if you could use scale. Let's find out. A wooden toy block can be modeled by a pyramid with a square base, as shown below. It's a square base, remember that. The height of the block is 17.4 centimeters. Looks like a dangerous block. And the square base has a side length of 8.2 centimeters. Now, does the 8.2 look like about half the 17.4? It actually does. Maybe a little less than half, which is exactly right. The block is made of solid oak, which has a density of 0.77 grams per centimeter cubed. What is the mass of the block to the nearest gram? Now, if I were to estimate this answer, I might, like if I didn't know how to do this problem at all, I might put this thing in a box, like a gift, pretend like it's a gift, get the volume of the box, use that to estimate the volume of the pyramid, and then use that to estimate the mass. But that said, I think it's actually better to really recognize that they give you plenty of formulas here, including the volume of a cylinder, general prism, sphere, cone, and pyramid. I do notice that the formula for the volume of a cone and a pyramid are actually the same formula. V equals 1/3 base times height, where B is the area of the base. 1/3 base times height, where B is the area of the base. Okay, so how do I deal with that? In this problem, we bring the formula in, and let's actually do some calculations. So V is equal to 1/3 base times height, where B is the area of the base, which is equal to, and they told us that it's a square base, okay? 8.2 times 8.2, which I believe is let me see, 64, 6, 5, 6, 1, 6, 7, 2, let me just do it. 6724. Yes. So what I did was I took the 64 and I added 1.6 and then 1.6 again, and I got 67.2. And then I did 2 times 2 is 4. Put that at the end. That's if you like doing some of that Vedic math. 7 equals 67.24. And so then the volume is equal to 1/3 of that 67.24 times the height, which is 17.4. And so if I bring that into the problem, so 1/3 times the answer, I'm going to highlight the answer and press enter so I get the number. And then, or you could do second answer, then times the height, 17.4, equals, so now the volume is equal to 389.992. Now, since the density of the pyramid is 0.77, I know that the mass is going to be smaller than this volume number, which, don't move away after I say this, because it eliminates 3 of the 4 answers, leaving this as basically the only possible correct answer. But as I said, don't move away quite yet, because there is a formula on this test, the Regents, that they do expect you to know. You're required to know it, despite the fact that it's a physics or chemistry or formula. That formula is density is equal to mass over the volume. Now, you might say, oh, I know that formula, when you mean you heard of that formula. But did you really memorize it and bring it into the problem before they, without the formula sheet being there to give it to you? So that said, the formula says that the density is 0.77 grams per centimeter cubed. We do have to check that we measured the volume in centimeter cubed. Let's see, centimeters for the length of the base and the width of the base, centimeter times centimeters, and the height is in centimeters. So we did measure in centimeter cubed. Now the grams per centimeter cubed is the density. The mass is an unknown number divided by the volume, 389.992. And so I'm going to multiply or cross multiply. Let me cross multiply on this one. Put this over 1 just so you see what I mean by cross multiplying. I know I already did one with cross multiplying, but that one didn't have the variable on top. So this one I'm going to cross multiply just for simplicity and for learning. M times 1 is equal to 0.77 times 389.992. Divide by that 1. You don't have to divide by the 1 because you know what happens when you divide by 1. Bring the calculator back. Put the numbers there. So 389.992 times 0.77 divided by 1 doesn't do anything. We get 300.29384. 300.29384, which is around 300 to the nearest gram. Okay? Which is exactly the only answer that was remaining. Number 14, in triangle ABC below, mid-segment DE is drawn. You do need to know what a mid-segment is. So let's just talk about that before we move on. A mid-segment is a line segment that bisects 2 of the sides of the triangle. So immediately, we know that's congruent to that, and that's congruent to that. And it does look like that's true, so far drawn to scale. Now, DE is x plus 3, and then AC is 3x minus 5. What is the length of DE? So what is the length of DE? And it's 28, 14, 7, or 4. Unfortunately, with this problem, there's no numbers to compare. So we are limited a little bit in what we can do for a process of elimination. But since they did ask for the length of DE, it is possible to test answers. For example, if you assume that the length of DE is any of your choices, your favorite choice 1, 2, 3, or 4, then you could plug it in, get X, and then get AC, and make sure that AC is double. But the thing that to know is exactly what I just said, that since the top triangle is BDE is similar to the triangle BAC, using the same proof that I used in a previous problem, we know that the triangles are that the sides are in proportion, and since BD is half of BA, the proportion is exactly 1/2, which means that the AC is equal to twice the length of DE. And so 3x minus 5 equals 2 times x plus 3. And look at the distributive property unavoidably appearing in the geometry regions. An algebra theorem appearing in geometry. But of course, the distributive property is one of the fundamental building blocks of math. It's actually a postulate. It's not even provable. It's a postulate. Our version of math uses that fact, the distributive property. So 3x minus 5 is equal to 2x plus 6. And now I'm going to subtract 2x, and I could stop there and do another step later, but since canceling out the plus 5, I'm canceling out the minus 5 with a plus 5 does not affect the subtracting of 2x. I could do those simultaneously, and I get that x is equal to, this cancels and this cancels, I get x is equal to 11, and so then DE, and a lot of students get this wrong because 11 would be a choice. You got lucky if you thought that 11 was going to be the answer because it's not one of the choices. But they will almost always include it as one of the choices. DE is equal to x plus 3. X plus 3, which is 11 plus 3, which is equal to 14. Let's mark these right. And let's go on to number 15. Triangle DUG, D-U-G, is an isosceles right triangle. Oh, that's a lot of structure. With the right angle at G. If DU is 10 radical 2, what is the length of GU? Okay, so I'm going to draw as best as I can an isosceles right triangle. Look at that. Thank you. With right angle at G. And DU, so I'm going to make this D and U. So we see that DU is the hypotenuse and G is the right angle. This is 10 radical 2. And then what is the length of GU? Some students might actually already know that it's 10. Great. But if you don't know why that's the case, then you might be stuck on this problem. But it is one of the fundamental things to memorize in geometry class. So I am not going to do this problem algebraically. Instead, I'm going to explain to you the 30, 60, 90 triangle and the 45, 45, 90 triangle. Okay. So again, why did I assume that this is a 45, 45, 90 triangle? Because it's isosceles, making those two angles congruent, and they add up to 90. Congruent angles add up to 90. You know, divide by 2, you get 45. 45. So if you have a right triangle, that's a 30, 60, 90 triangle. And then if you have this side is length x, then the shorter side of the 30, 60, 90 triangle is going to be a half x. And then the longer leg of the triangle is going to have length x radical 3 over 2. So that's the 30, 60, 90 triangle. And then the 45, 45, 90 triangle So this is 45. This is 45. Actually, I don't, there's something I don't like about it. It's just not isosceles enough. If I just extend that a little bit, and then I delete. Let me see if I could delete that. So there we go. So if I do that, that looks more right, 45. Then this side and this side are going to be congruent. And if this hypotenuse is length x, then the bottom side has length x radical 2 over 2. And the left side has also length x radical 2 over 2. So these are really triangles that are fully worth memorizing for, in general, for real life. Why do they keep going for these problems? There's with these exact triangles. There's two reasons, and one is that they're easy to work with, but there is another reason. They actually just come up in real life all the time, unavoidably. Because in real life, if you're doing geometry in real life situations, you often have two lengths that are congruent, and one way that can manifest is the 45-45-90 triangle. And another way is if you have three sides congruent with an altitude in your figure, then you get a 30-60-90 triangle. So these come up in real life situations all the time. And so that's two reasons why these are taught. And so, but that said, I didn't prove these formulas. I just stated them because it is something that you want to memorize. If this is equal to 10 radical 2, then the question is, what is this equal to? Well, it's equal to 10 radical 2 times radical 2 over 2, and the radical 2 times radical 2 is equal to 10 times, well, radical 2 times radical 2 is 2 over 2. The 2 over 2 cancels, and this is equal to 10. Exactly like we suspected. Why some students got this problem right away? Because sometimes students write it as x and x radical 2 over 2 and x radical 2 over 2. Some teachers write it as like x and x radical 2. So that's why some students got it quicker. But that said, is it better to do it that way? I actually don't think so, because this also contains the sine and the cosine in the problem. And so does this. So benefits and drawbacks. Number 16. In triangle RST below, RS is equal to 9, okay, and RT is equal to 8. And it looks ever so slightly shorter than the 9, so far drawn to scale. And the measure of angle TRS is 55 degrees, look ever so slightly smaller than a 60-degree angle. Fine. What is the area of triangle RST to the nearest square centimeter? Is it 59, 36, 29, or 21? A clever trick that I use for my students, a lot of students insist on just doing base times height over 2 no matter what the situation is. But the thing is that base times height over 2 only works if you have a base and an altitude height. And then, which then you divide by 2. But there is a intuition fixer fact that the answer to an area is often very close to 2 side lengths divided by 2. But 2 side lengths multiplied divided by 2 is a cap on the area. So I'm teaching you the cap. So max of the area of RST is equal to 8 times 9 over 2, which is equal to 36. So this is a cap. But notice it actually eliminates, well, it eliminates 59 for sure, but it also eliminates 36 because this is not a right triangle. But how is this an intuition fixer? One, because we established the thing that students assume all the time is actually false. But the part that's an intuition fixer is also that the answer is often very close. And in fact, when is the answer not close to it? When the angle in between the two sides is tiny. And so we could actually say, since this angle is not tiny, tiny means like 30 degrees or lower. In this case, since this angle is not tiny, the answer is going to be close to 36, which makes 29 a very nice looking answer. So intuition fixer, it's not going to be 8 times 9 divided by 2, because the R 55 degrees is not a right angle, 90 degrees. However, the answer should be close to that 8 times 9 divided by 2. And so 29, choice 3, 29 is looking mighty fine. And so how to actually do this problem, though, there is a theorem. If you have a triangle, let's draw this one in this blue. If you have a triangle, now you don't know if it's a right triangle or not, okay? But you know this angle A. And you know this side, let's call it B, and let's call this length C. Now, I'm gonna change those letters. No, I'm not gonna change those letters because that's often the letters that are used. Okay. If A is a 90-degree angle, notice that sine A is sine 90, which is 90. In fact, that if you replace the sine 90, which is 1, with just sine A, the formula for the area of the triangle is actually equal to 1/2 BC sine times sine of A. And that is a fundamental formula that they're using more and more on this test. So you do want to use it. Are there other ways around it if you don't know how to use this formula? There are. Like for example, you could draw an altitude going this way. This is just if you don't memorize this formula and you feel like you can't, you could draw an altitude going that way. Call that x, and now you have a right triangle with a hypotenuse and an angle, and you could use cosine to get the length of the altitude, and then you could use 1/2 base times height to get the area. But I'm going to use the area of the triangle being 1/2 BC sine A, so that's equal to 1/2 the lengths of the two sides, 8 times 9, times the correction factor, which is the sine of the included angle, sine of R, sine of 55. Okay? And so I go to my calculator. So 1/2 times the 8 times the 9 times the sine of the 55-degree angle, which is, enter, approximately 29.48947,359, which is again to the nearest square centimeter. It's approximately 29. Let me minimize this so you see I wrote all the digits, and it's approximately 29, which is exactly what I had said. Nice intuition correcting fact. Some students think again base times height divided by 2, which is correct, but they take any two side lengths to be the base and the height, which is not correct. But in fact, you can correct that by saying that the area is maximized by 8 times 9 divided by 2, and most of the time the answer is close. The exception is when the included angle is tiny, again 30 degrees or lower or so. But there's another case if the angle is actually very obtuse, close to 180. So close to 0 or close to 180, then you could actually then say, well, actually the area is a lot less than 8 times 9 divided by 2, and then that allows you to eliminate answers too. Nice little intuition picture. Now, number 17 will secure us a passing grade on this test. So we are almost passing this test. One more problem, and we are going to pass. So this is it. Congratulations to making it making it to this point. We have triangle ABC is dilated by a scale factor of 2 to map onto its image triangle RST on the set of axes below. What are the coordinates of the center of this dilation? Is it 1, -1, or 2, 1, or 3, 3, or 0, 0? And the thing to know about dilations is that they preserve the direction of the dilation. So it preserves parallelism and it preserves the direction of a dilation. So if you make a ray from the center of dilation to a point and then dilate that point is going to be on the same line, which means if we actually draw a line from the corresponding points, again, the order of the vertices matters, triangle ABC and triangle RST. So R corresponds to A, S corresponds to B, and T corresponds to C. If we draw a line segment, a line through R, going through A also, it's got to fix it. Now, I'm drawing with the software. You might say, oh, I don't have software to draw perfectly straight lines, but you do have a straight edge, okay? So I'm going to draw that line again. Why is it not doing it? Okay, let me try it again. I think I'm drawing too long. There we go. And then I keep going. So the line going through RA. Good. Now I'm going to draw another line going through SB, and this is probably going to confirm my center of dilation. Okay, that didn't do it. It's not being nice. Come on. Yes. Okay. And there's my center of dilation. It's probably going to be that point. And now I'm going to check my answer by drawing a straight line through C and T. Nope. Again. A different color. Let's go for black. There we go. Through CT. And look at that. We have a nice center of dilation, the point 2, 1. There are reasons to eliminate some of these answers, like, B, 3, 3 didn't make sense because if we were dilating through B, then point S would have been on B, which doesn't happen. 0, 0 could be eliminated because of the fact that R is right up on the y-axis, so that A would be on the y-axis if the center of dilation would be 0, 0. So some of these can be eliminated and leaving, two choices. But that's we are at number 18. What is the perimeter of triangle ABC where the vertices have coordinates A, -2, 3, B, -2, 1, and C, 6, -1? If you need to, you can use the graph paper in the back, okay? But I'm going to draw just a quick axis, okay? When I say the graph paper in the back, what do I mean? If you go to the back of the test, there's free graph paper here that you could use. It's not graded, so you could use it as much as you want, okay? But let's see, -2, 3. There we go. -2, -1. And 6, -1. Okay, so that's going to be point A. It's going to be point B. It's going to be point C. And this is, again, 6, -1. This is going to be -2, -1. Let me make that a little bit. So a little bit more visible. Ah, come on, what just happened? Why is that? Okay. Why is it hopping? I don't know why it's hopping like that, but okay. -2, -1, and A is -2, 3. Okay, so I have the coordinates, and they want the perimeter of this triangle. And so how do I do this? Suppose I struggle with some of my formulas. There is something to notice that A and B are above each other, so I can actually get the length of AB by just kind of counting 1, 2, 3, 4. So this length is 4. And I could get this length because B and C are actually next to each other, in a sense. They have the same y coordinate, 1, 2, 3, 4, 5, 6, 7, 8. So this length is 12. So the perimeter of triangle ABC is got to be greater than 12. But what about, I see a few that are greater than 12. So there is the triangle inequality, which implies that AC is going to be less than the sum of AB plus BC. So AC is going to be less than 12, which actually eliminates 92. Again, the answer, less than 12 means the whole perimeter is less than 24. 16 radical 5 is greater than 32 because it's greater than 16 times radical 4, which is 16 times 2, which is 32. So we've already eliminated two of the choices, and then 16. The perimeter would be 16 if the hypotenuse AC. I said hypotenuse but these are a vertical line and a horizontal line, so they do have perpendicular sides, right angle. If the hypotenuse was 4, but the hypotenuse is greater than 8, so this one's already too small as well. So we've eliminated just by comparison the answers. But how do I actually get the length of AC? You do need to know how to get AC using algebra, because of the fact that this could easily be a part 2 question. Now, you're noticing that I'm showing work on basically every single problem. That's an unavoidable thing if you want to get the best grade possible. And again, I mentioned why it's not the best advice to focus only on the part 1s. Well, because one, we noticed that you actually do need more than half of the problems if you only focus on the part 1s. You're very unlikely to pass if you only focus on the part 1s. But the thing is, focusing on the part 1s means showing work on the part 1s. But the part 1s and the part 2s, and definitely parts of the part 3s and 4s, look identical. If I in fact crossed out the multiple choices, this is a part 2 question. Part 2 questions and part 1 questions are essentially equivalent. So if you're focusing on the part 1s in quotation marks, then you're focusing on the whole test by showing all work, which means you should focus on the whole test. Okay, that said, how do I get the length of AC? I could get it by the distance formula, or I can get it by the Pythagorean theorem, since this is a right triangle. The hypotenuse is actually B in this case. So, but this is weird. So we got that AB squared plus BC squared is equal to AC squared. So AB squared is 4 squared plus BC squared is 8 squared, and that's equal to AC squared. And so we get 16 plus 64 equals AC squared, which is, so 80 is equal to AC squared. Take the square root of both sides, take the square root of both sides, and you get radical 80. So AC, now you do have to simplify radicals, even in this class. Look for the largest perfect square factor of 80, which is 16. Radical 16, radical 5, which is equal to 4 radical 5 is AC. So let me cross out that B because it almost looks like a 6. This is 4 radical 5. Okay, so the perimeter is equal to 4 plus 8 plus 4 radical 5, which is equal to 12 plus 4 radical 5, which is choice 4. Number 19, in the diagram below, GT and PF intersect at E, and angle P is congruent to angle F. Big deal. That's a big deal. Because that implies a lot of things. And so then which equation is always true? Is it that PE over FE equals FT over PG, or GE over TE equals FT over PG, or PE over GE equals TE over FE, or PE over FE equals PG over FT? That's a whole lot of letters to memorize or think about. That's a lot. That's a lot. So the right way to go about it probably is not like a super analysis of the exact ordering for every single choice. What's most likely is that we want to actually use some sort of theorem. And if we don't have a good theorem, we can't say much. And so when do we have sides that are proportional to each other? When we have similar triangles. And in fact, these two triangles have one pair of angles that are congruent, and this pair of angles, angle PEG, is congruent to angle TEF, because, why? Well, because vertical angles are congruent. So now these two triangles have two pairs of congruent angles. So triangle PEG is similar to triangle, now I gotta write these in the correct order. P corresponds to F, E corresponds to E, and G corresponds to T, in that order. And so when we write the proportions, we could actually identify them as correct if they are in the correct order and they are either on the same side parts of the same triangle or on the same side parts of opposite triangles. So we have PE is vertex 1 and 2 of the left side triangle. So I'm going to say 1 and 2 on the left side triangle. FE is vertex 1 and 2 on the right side triangle. And now FT is vertex 1 and 3 on the right side triangle. Not looking promising because now we have left over right equals right over, I guess, left. 1 and 3 on the left side. So the fact that the lefts are diagonal to each other and the rights are diagonal to each other means that this answer is not correct. If we do the same thing for choice 2, let's use the green. GE, which is 3 and 2. 3 and 2 on the left side. And TE, which is 3 and 2 on the right side. That's equal to FT, 1 and 3, again on the right side, and PG, 1 and 3 on the left side. And this again, the left sides are on the same side, and the left sides and are on opposite parts of the fractions, and the right sides are on opposite parts of the fractions. So this one's not correct. Same deal for for choice 3, PE, which is 1 and 2 on the left side triangle, GE, which is 3 and 2 on the left side. Now they got left over left, which is okay on the same side. Now on the right side, we got TE, which is 3 and 2 on the right side. And we got FE, which is 1 and 2 on the right side. So right side over right side is okay, and left side over left side is also okay. However, now we have, what we have is 3 and 2 are on opposite parts of the fraction. Bottom on the left, top on the right. And 1 and 2 is top on the left and bottom on the right. So this one's not correct. Leaving most likely, hopefully, the correct answer being choice 4. And let's actually compare. PE is vertex 1 and 2 on the left, and PFE is vertex 1 and 2 on the right. Here, vertex PG is 1 and 3 on the left, and FT is vertex 1 and 3 on the right. Now look at the way we can highlight this, right? If we highlight the lefts, we got the lefts on both on top, the rights both on bottom, right? Then if we highlight the numbers, the 1 and 2, oops, I meant to highlight that. The 1 and 2 are both on the left side of the equal sign, and the 1 and 3 are both on the right side of the equal sign. So it makes this kind of tic-tac-toe pattern. That's actually the symbol, the hashtag symbol that identifies the correct proportion. So if you look for left and right, and also the vertex order, making the hashtag symbol, then you got the right answer. That's actually how to do this problem, and many of the problems, even the ones that look a lot more difficult than this. Okay. On that note, let's go to number 20. A section of sidewalk in the shape of a rectangular prism is being replaced. The sidewalk is 10 feet long, 4 feet wide, 4 inches deep. A brand of concrete mix yields 0.6 cubic feet of concrete per bag. What is the minimum number of bags of concrete mix that must be purchased to complete to replace the sidewalk? Is it 22, 23, 26, or 27? So the sidewalk portion is 10 feet long, 4 feet wide, 4 inches deep. So, but that said, I know that the yield is 0.6 cubic feet, which is less than 1 cubic foot. So whatever the volume is, I know that the number of bags needed is going to be greater than the cubic feet. Now these numbers are pretty close to each other, 22, 23, 26, 27, so that doesn't quite let me eliminate any choices. But if I do the volume, now notice that this says 4 inches deep. So you do need to know that 12 inches. So you do need to know that 12 inches is equal to 1 foot. So that 4 inches, which is a third of 12, is 1/3 of a foot. So the volume is equal to, now the volume of a rectangular prism, I would hope that you know this by heart, but if you go to the formula sheet again, the volume of a general prism is volume equals base times height, which is B is the area of the base. Okay? So V equals base times height, where B is equal to the area of the base. Or you could remember that the volume of a rectangular prism is length times width times height. But I do get that the volume is equal to the area of the base, which is length times width, 10 times 4, times the number of feet in the height, 1/3, which is equal to 40/3, which is equal to 13.3 repeating. So and I said that the number of bags it's going to take is going to be more than the volume number, which unfortunately, though, all of these numbers are bigger. But how can I deal with the volume of concrete? Now, this is if you divide the volume divided by the volume per bag, notice that if you cancel out volume as units, you get 1 over bags, which is a number of that has units of bags. So this is the number of bags. So this is equal to 13.3 repeating, or 40/3. I'm going to do the 40/3 in parentheses. 40/3, because the 0.3 repeating is kind of whack. Divided by 0.6. And now I'm going to get the calculator out. Parentheses, 40/3, close parentheses, divided by 0.6. And I get exactly 22.2 repeating. Well, I do need to purchase enough bags to fill that extra 0.2. So I do need to purchase another bag. So I need 23 bags. 23 bags, which is choice 2. Okay. Now, number 21, the line 4x minus 6y equals 24 is transformed by a dilation of scale factor 3 centered at the origin. Which equation represents the image of the line after this dilation? Okay, is it y equals 2/3 x minus 12, or y equals 2/3 x minus 4, or y equals 2x minus 12, or y equals 2x minus 4? So the thing, if you recall, dilations preserve parallelism. Dilations preserve parallelism. And so then they preserve slope. Since two lines that are parallel to each other have the same slope, dilations do preserve slope. Okay? So one way I could do this problem is by starting off by solving for y. So 4x minus 6y is equal to 24. If I subtract 4x, I get that negative 6y is equal to negative 4x plus 24. Divide by negative 6, divide by negative 6. And I get that y is equal to 2/3, positive 2/3 x minus 4. Okay, so that's the equation of the original line. Okay? That's the equation of the original line. So the answer, since the answer preserves parallelism, the answer can't be choice 3 and 4 because these have m equals 2, which is not equal to 2/3. They don't have the same slope. So those are wrong. There's another reason I can actually already eliminate this one, but why can I eliminate this one? The only way to dilate a line and get the same exact line back is if you dilate over a point that's in the line. That's a common thing, a question that they ask, so you do need to know that. If you dilate a line through a point in the line, you get the same exact line back. If you, however, you dilate a line through a point not in the line, then you get a different line that's farther or closer depending on the dilation factor. So this is dilated over the origin. Okay, so if I have a axis dilated over the origin, the original line passes through negative 4 and looks like this. Does not look like that. It looks like this. Then when I dilate by a factor of 3, every point on the line is going to be 3 times farther, including the y-intercept. So 3 times farther, I end up at negative 12. And so the dilated line is going to go through that point. And I'm not going to wait for that to make that nice and straight. So the y-intercept of this dilated line is negative 12, and it's got the same slope, and it's got a y-intercept of negative 12. So the one that has that is choice 1. I already knew that this one was going to be false, so I could have crossed it out here because, again, the origin is not at on this line, so the dilation was going to be strictly farther away. Number 22, a rhombus is graphed on the set of axes below. Now, this shape does, in fact, look like a rhombus. It does. And, in fact, because it's on graph paper, it has to be, in fact, a rhombus. It has to be, rather, drawn to scale. And when it's on graph paper, it has to be drawn to scale. Which transformation does not carry the rhombus onto itself? Is it a rotation of 180 about the origin, or a rotation of 180 about the point 10? Or a reflection over the line y equals 1/2 x minus 1/2, or a reflection over the line y equals negative 2x plus 2. I want to, for all people who are writing problems, this I recommend italicizing the entire phrase "does not just the word "not," because there's something about the word "not" for people like me. I don't know if it's everyone. I'm a little bit dyslexic, and I know that a lot of people have slight reading problems. But when I was a kid, I remember they highlighted or italicized the word "not," and it causes your eyes to just slide over the word "not." So if they actually italicize "does not" instead of just the word "not," I think that would be better. That's my advice to the Regents creators, although who knows if they listen to this. That said, I also, when I was going through this, I literally forgot about the fact that it said "does not," and I did make a mistake. So if I'm able to make the mistake that it says "does not," are you likely to do it? Sure. So how do we do it? Does not. And I'm going to write the word "not" in big letters, just so that when I do this problem, I keep it in mind. Now, there are some that I could eliminate. How can I possibly eliminate? Since it says "not," it means that 3 out of this 4 transform the rhombus onto itself, and only one of them does not. You can't rotate a figure other than the 360-degree rotation, because that's the identity rotation, and it's equivalent to a rotation of 0 or not moving the thing at all. Or you can't rotate a figure about 2 different points and rotate the figure onto itself. It's not physically possible. So one of these 2 has to be incorrect, or has to be not carrying the rhombus onto itself. Therefore, and since the problem can't have two answers, it can't be that one of these doesn't, but also one of 3 and 4 doesn't, because only one of the 4 choices doesn't rotate the figure onto itself. And now we have a passing problem. It turns out, if you didn't know that and you decided to check your answer, checking your answer gives you the answer to this question. For example, suppose that you didn't know whether a reflection, one of these reflections, does or does not rotate the figure onto itself. Well, what you could do is you could actually graph the lines, okay? And you get, let's see if it lets me, good. You get this line, which is y equals 1/2 x plus 1/2, which you see goes through the two vertices. It's one of the two lines of symmetry of this figure. So that's not the answer. That proves that it's not the answer. But also, if you graph the line y equals equals negative 2x plus 2, let's see, good, make it perfect. Now, I'm using software to make the line perfectly drawn. You have your straight edge to do it. This line is also a line of symmetry going through these two vertices, so that proves that that's not the answer. So how does it show which of choice 1 and choice 2 is the answer? Well, the rotation that rotates the rhombus onto itself has to also preserve the lines of symmetry. So it has to be a rotation about this point. So a rotation about this point, 1, 0, does rotate the figure onto itself. And they said does not. I'm going to write the word does, and does here to super emphasize that I'm crossing out the ones that do carry the rhombus onto itself. And the only one remaining rotating about the origin is the only one that does not rotate the rhombus onto itself. You can do that also by rotating any of the vertices by 180 about the origin and seeing that it just doesn't go to the right place. But we just proved that the rotation over the point 1, 0 does rotate the rhombus onto itself. Number 23, in the right triangle Hay, altitude AL is drawn to hypotenuse HY, and all of that seems to be true. And it does, the right angle looks like a right angle. This does look like an altitude because it looks like a right angle. They told us it's an altitude, so I'm going to label immediately that these are right angles. If HY is 25, so across, that's 25, and you got YA is 20, then the length of AL is it 9, 12, 15, or 16? Now, everything, like I said, the angles are drawn to scale, but the second piece is that the 20 is shorter than the 25, and it's more than half of the 25 by a lot. So this diagram is actually drawn to scale. And so what that means is we could use scale to estimate AL. AL looks like it's more than half of 20, which eliminates that one. But not a lot more than half of 20. This is 3/4 of 20, so it's probably too big, and this is more than 3/4 of 20. It's probably too big. This 12 is looking mighty fine as an answer, but this is not. This is using scale to tell us what the answer most likely is. Let's actually think about how to actually do this problem. There is a theorem that you need to know. If you have a right triangle, and you draw an altitude from the right angle to the hypotenuse, then you actually make 3 similar triangles. And the proof of it is it's not difficult. I highly suggest you memorize that. But the proof is not difficult. Angle H, the 3 right angles correspond to each other. So all 3 pairs of right triangles have 1 pair of angles congruent, the right angles. Then angle H corresponds to itself on the left side triangle and the outside triangle. So that left side triangle and the outside triangle have 2 pairs of congruent angles, so they are similar. Now the right side triangle has this angle in common with the outside triangle. So the right side triangle and the outside triangle also have 2 pairs of angles congruent, so they are similar as well. And then by the transitive property, the left side triangle and the right side triangle are also similar. So this is These are three similar triangles, which means that you could use a whole lot of proportions to figure out the corresponding the lengths. So what can I do to get the length of AL? There are a few ways of doing it, but before that, I want to actually establish the proportions that are true about these triangles. Remember that when we write the proportions, we actually want to write the proportions in with the vertices in the correct order, which means that you want to write the corresponding vertices in the correct order. So I'm going to say the outside triangle, the left side triangle, and the right side triangle. Well, the right angles definitely correspond to each other, so I'm going to write those in black. For the outside triangle, that right angle is at A. And for the left side and the right side triangle, both right angles are at L. Okay? Now, for the angle H on the outside triangle, H is an angle of the left side triangle, so H corresponds to H in the left side triangle. And now, suppose I don't know which angle corresponds to H in the outside and the right side triangle, which is okay. Third, the angle Y of the outside triangle, I don't know which angle that corresponds to on the left side triangle because angle Y is not on the left side triangle, but angle Y is an angle of the right side triangle, so angle Y corresponds to angle Y. And now I have two of the three for the left side and the right side corresponding to the outside triangle. Now, which one corresponds to which for the remaining vertex? Well, the left side triangle only has one remaining vertex at vertex A. So vertex A corresponds to vertex Y in the left side triangle. And same vertex, the only missing vertex in the right side triangle is also vertex A. So vertex A corresponds to vertex H in the other two triangles. And now I have all three triplets of corresponding vertices, so I can actually make ratios of sides. Now I see that I need to make a ratio involving AL and a known side. AL is a side of the right side triangle, and so is AY. So I'm going to make that ratio of the right side triangle, that hypotenuse AY divided by AL. Now think about the order that I put those in, AY over AL. This is the right side triangle. I put AY on top, and then I put AL on bottom. So when I make the same ratio for another triangle, I have to put it in that order. I see that on the outside, I have a ratio. I have one of the outside triangle sides, HY, and it's the hypotenuse corresponding to AY. So I'm gonna put them in that order in a ratio for the outside triangle, HY over AH in that order. Okay, so I got that's equal to HY over AH, and I plug the numbers that I know into this equation. We're gonna have a little surprise at the end. Hold on. AY is equal to 20 divided by AL. We don't know AL, but it's okay that we don't know it because that's what they're asking for, isn't it? Right? It's okay that we don't know the thing we're asking for because if we knew it, we'd just answer it. But that's equal to HY. And then that's divided by AH. And if you look, we might panic a little bit. We don't actually know AH. What do we do? But there is something that we could do. We know two sides of the outside triangle. We know the hypotenuse 25 and we know a leg 20. So we could actually use the Pythagorean theorem, HA squared plus AY squared. That's equal to the hypotenuse squared, HY squared. And so you could plug in the known values. AY is 20 and HY is 25. I'm actually not going to do that because what I'm going to use is a nice Pythagorean triple. I know the 3, 4, 5 Pythagorean triple. If I multiply all of the sides by 5, I get 15, 20, 25, so that this length HA is 15. And if you didn't know that, you could use the Pythagorean theorem to get the length of HA. And there are many other ways to get other lengths as well, other ratios. There's, so many ratios that you could create based on these this triplet of corresponding vertices. But I know now that AH is 15. And sorry, I wrote HY here. I meant to write 25 here because we know that one, 25. So the only one that we didn't know was AL. If I cross multiply, I get that 20 times 15 is equal to 25 times AL. And if I divide by 25, I go to my calculator and I get that AL. I do go to my calculator, I do 20 times 15 divided by 25, and I do get 12. So AL is, in fact, the thing that I suspected, slightly more than half of 20, which is 12. Okay, number 24. Square ABCD has an area of 36. And by the way, after 24, we got a perfect part 1. So you should congratulate yourself for getting to this point. And listen, I know you can do it. I know you can do well on this region. So I'm really proud of you for going through the process of going through this video and just trying to do your best. That's what we need you to do. Do your best. I know you could do it. Let's keep at it. Number 24, square ABCD has an area of 36. If the square is dilated by a scale factor of 1/2, centered at A, what is the area of its image? Is it 9, 18, 72, or 144? Since I'm dilating by a scale factor of 1/2, I'm shrinking the square, which means that it can't be 72 or 144 because those are bigger than 36. I'm already down to 2 choices. So how do I do this problem? There's actually a lot of ways of doing this problem. The linear square cube law says that if the lines are scaled by a factor of 1/2, then areas are scaled by a factor of 1/2 squared because areas are 2-dimensional. The exponent is 2. So the scale would be 1/2, which is the scale factor. That's actually usually the scale factor D. So lengths scaled by a factor D, little d, for dilation. Dilations or R. Let's use R. I like R. Okay? Length scaled by a factor of R. That means that areas, notice that all lengths are 1-dimensional. And the exponent on R to the first is a 1. That's actually a theorem. The areas are scaled by a factor of R squared. Notice that areas are 2-dimensional. And that exponent 2 is the same 2, the dimension of the figure. And volumes are scaled, which volumes are 3-dimensional. Volumes are scaled by a factor of R cubed. Okay? So the area is scaled by a factor of 1/2 squared as 1/4. 36 times 1/4 would be your answer. So 1/2 squared is equal to 1/4, and so the area is equal to 36 times 1/4, which is equal to 9. Now, could I have done this another way? It's a square. Area 36, so side lengths 6 and 6. Divide those by 2, 3 and 3. Area 3 times 3 is 9. Now, interestingly, the scale factor thing that I told you about, I said that the scale factor for the area and the volume have the exponent, which is equal to the dimension of the measure. And you might say, how do I prove that? But actually, it goes the other way around. Notice that you've never defined dimension, right? For most of you, you've never defined dimension. So the way we can define dimension to start is if an object has some self-similarity or something else, some other property that allows us to scale it easily, then the exponent on the scale factor is the dimension, the definition of the dimension of the figure. So you could actually take that as the definition of the dimension. And if you're wondering how we define fractals, fractals have a dimension which is a fraction. You're like, how could a thing have like a 1.3 how could a figure be a 1.3 dimensional figure? How could a figure be a 2.8 dimensional figure? How could a figure have a dimension of like log 3 divided by log 2, which is a common thing? But the answer is because that's the exponent of the scale factor. The exponent of the scale factor is defined as the dimension of the figure. So when you see fractals with really cool designs in them, that's where the dimension comes from. Okay? And yeah, we just got a perfect part 1. Congratulations. That's it. Perfect part 1. And to celebrate, we can recognize that every single time we use scale, we got the question right by just guessing. So we could cross out the words not necessarily. Now that we buy in, we know that this means almost definitely. Number 25, triangle D prime, A prime, N prime, Dan prime is the image of triangle Dan, D-A-N. After a translation, explain why triangle D prime, A prime, N prime, rather, must be congruent to triangle D-A-N. So how to go about this problem? This is, you kind of just have to know which transformations preserve congruence. Translations, rotations, and reflections preserve congruence. And so that's the thing. So triangle D prime, A prime, N prime is congruent to triangle DAN because translations preserve lengths and angles. Angle measures. With that, let's hop over to number 26. The table below lists 5 metals and their densities. So the metals are zinc, tin, copper, iron, silver. The densities are 7.14, 7.31, 7.86, 8.96, 10.5. I don't memorize that. I just keep that in mind so I can go back to it later. I don't try to keep it. No, I don't try to keep it fully in mind. That's actually false. I read it once and then go back to it later. I just read it once so that the subconscious part of my brain could do some analysis of it, okay? So now, next, a solid metal cube has an edge length of 5 centimeters and a mass of 982.5 grams. Using the table above, determine and state the type of metal from which this cube is made. So another one, they want us to know the formula density is equal to the mass divided by the volume. Density is equal to the mass divided by the volume. So that's what we got to do. We got to find out. We know the edge length, and so that's got to be able to give us the volume. And we know the mass is 982.5. Well, the volume, again, this is a solid metal cube. So the solid metal cube has a volume of a side cubed. Now, if you didn't know that, I do wish you did know that. Again, it does help to know that. But if you didn't know that, you can once again go to your reference table and see that the volume of a general prism is base times height, where B is the area of the base. The base is a square, 5 times 5, and then the height is h, 5 times 5 times 5. So S cubed, which is equal to 5 cubed, which is equal to 125. And so the density is equal to the mass, 982.5 divided by the volume, 125, which is equal to, now I'm going to go to my calculator, and I'm going to do this arithmetic on there, but I do see that it's probably not silver. If you just write the name of the metal, you get a point. So you have a 1 in 5 chance of getting a point. You should, if you have a 0 clue, you don't remember the density formula, just write a metal. However, you should try to remember the density formula. That's the better way to do it. Remember, density is equal to mass over volume. So 982.5 divided by 125. And we get 7.86. And so then the metal is iron. Okay? You don't have to use full sentences. You could just state. They said determinant state. Okay? The metal. Number 27. The endpoints of segment CAS are C, -3, 1, and S, 7, 6. Determinant state the coordinates of point A such that the ratio of CA to AS is 3 to 2. The use of the set of axes is optional. Okay, so I'm going to graph this -3, 1, and I'm going to graph the 7, 6. Okay? -3 and 1. And the 7, 6. 1, 2, 3. So this is -3. This is 1. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6. Okay, so that point is right there. Then I'm going to draw the line segment from these 2 points. Okay, good. And now, so this is C, this is S, right, in that order. Let me just make sure. C and S. And now I need A, so that CA to AS is in a ratio of 3 to 2. So A has to be slightly closer to S and slightly farther from C. And in fact, if I divide this line segment into 5 parts, and then 3 parts of it ends right here, so that's A. So if I state the coordinates of A right there, that's at least a point. Oops, I almost said it wrong. 3, 4. That's at least a point. So why is that not 2 points? Well, it's not 2 points because I haven't verified that the ratio of CA to AS is actually 3 to 2. Okay, so how can I actually calculate that? So I have the coordinates of C is -3, 1. I have the coordinates of S are 7, 6. And what I could do I could do the distance formula, or I can count the vertical distance and the horizontal distance and show that the vertical distance and the horizontal distance are in a ratio of 3 to 2. So that second way is pretty nice. So I'm gonna show that the second way. If I go this way, I go 3, and if I go this way, I go 6, and if I go from A to S, I go this way, I go 2, and I go this way, I go 4. Now with these numbers, I can also go up from C to S. I can go up 5, and I could go to the right 10. And so I could do ratios of the sides. I could do 3 over 6. That's also equal to the 2 over the 4, which is also equal to the 5 over the 10, which is equal to 1/2. They're all equal to each other. Okay? The ratios are equal to each other. That's important. But also, the numerators, 3 to 2 is equal to 3 to 2. And also 6 to 4 is equal to 3 to 2. So CA to AS is equal to 3 to 2. And that's 2 points. That's not a common way to do it, but I think it's probably the easiest way to do it. It doesn't require the distance formula. And this is a much simpler version of what we wrote. It's memorizing the shortest possible route to getting 2 points isn't the right way to go about it, because did we write just barely enough to get the 2 points? Probably not. But notice that this one does the same exact work that we just did. So there is a valid way of doing the problem. Here's another one that does exactly the same thing. Okay? So that said, we're going to go on to number 28. The ramp shown in the diagram below has an angle of elevation of 4.8 degrees. 4.8 degrees. The ramp is built to a landing 0.6 meters above the ground. Determine and state the length of the ramp to the nearest tenth of a meter. Now, this is one that's really tough to estimate, but if I chose a number that's just much bigger than 0.6, I might get lucky. I doubt that I would get that lucky, but if I did, well, then I get it. But here's what we got to say. The length of the ramp. So this is what we got to do. We got to do the length of the ramp from here to here. And this is a right triangle, right? This is the hypotenuse. And this is the leg opposite. The forward 0.8 degrees angle. And if I remember SOHCAHTOA, the ratio that uses opposite leg and hypotenuse is this one. Sine of, I'm going to call this point A. Sine of point A is equal to opposite leg over the hypotenuse. And so that I got sine of 4.8 is equal to the opposite leg, which is 0.6, divided by the hypotenuse. I'm going to call that ramp. And then I'm going to put this over 1 so I could cross multiply. And I got that ramp times the sine of 4.8 is equal to 0.6. So if I divide by the sine of 4.8, divide by the sine of 4.8, I got my answer. I got the ramp length is equal to a length of what the calculator says. Let's see what the calculator says. 0.6 divided by sine of 4.8. And I got 7, and this is where the muscle memory that I told you about before is going to matter. So this is where I said that I write all the digits and then round. I say 7.17036, nope, 0356, 884, okay? Minimize the calculator now. I write all the digits and then I circle what it tells me to round to, and then I round. It's approximately 7.2. They gave the units 1/10 of a meter. They gave the units in meters, and so I don't have to give the units. And there we go. So the ramp is just approximately 7.2 meters. Okay, let's hop to number 29. Angle KML is the vertex angle to isosceles triangle KLM. So that's the vertex angle. That means that this angle is congruent to this tiny angle. And then the side LM, so that makes that these two sides are congruent. Side LM is extended through vertex M to point N. So we got the second angle here, which we don't know the measure of. And they say if the measure of angle K inside there is 15 degrees, determine and state the measure of angle KMN. If you just state that it looks like double. So if you just state the number 30 degrees, turns out you'd be right and you'd get a point, which is great. This diagram does seem to be drawn to scale. So estimating, because the 15-degree angle is a pretty tiny angle, so estimating that the angle measure as being double the 15 would actually get you the 1 point. So again, if you just wrote 30 degrees, that's a point. It's not 2 points, and we're trying to get 2 points. We're trying to get a perfect grade. So we're going to do it the way they expect it. There is a theorem called the high school exterior angle theorem, and says that the measure of an exterior angle is equal to the sum of the measures of the opposite interior angles. So 15 plus 15 equals the 30 degrees. And so you could do it by the high school exterior angle theorem. There is another way to do it. If you know that the measure of those two angles are congruent, 15 and 15, then the measure of that angle is 180 minus 15, which is equal to 150. And then this angle measure is 180 minus the 150, which once again is equal to 30 degrees. Any of these two ways of doing the problem, the purple way or the green way, is valid, but the measure of angle KMN is equal to 30 degrees. Circle 30 degrees. and I get 2 points. That's great. High school exterior angle theorem or angle chasing. Both get you the same answer. Number 30, in the diagram below, circle L, the area of the shaded sector KMN is 7.5 pi, and LK is 5. So and then determine and state the degree measure of angle KMN, the central angle of the shaded sector. They did not say to the nearest whatever, so I strongly suspect that it's either going to be a nice integer or a nice decimal. Okay? So if you just visually guess based on scale, you may or may not get it right. We don't even know yet if it's drawn to scale. But if you were to guess, I mean, it doesn't look quite to be a 120 degree angle. It definitely looks to be bigger than a right angle. So if you guess something bigger than 120, it was bigger than 90 and less than 120, you may get lucky. Very small chance of getting lucky in this case, though. So how are we going to do this problem? We're going to do it by proportional reasoning. There is a formula that does this, but the truth is that there's a proportional reasoning method that works across all of these types of problems. And so it's the part over whole proportionality equation. Okay, so this angle, I'm going to call this X, that we're looking for. We're looking for angle, well, actually, we have the measure of angle L. Let's just use the measure of angle L. So what is the part over whole proportionality equation? Well, let's see. If I have an angle of 0, then I have an area of 0. If I have an angle of some angle, then I have some area. If I double the angle, I double the area. If I triple the angle, I triple the area. Quadruple the angle, I quadruple the area. That means that the central angle measure and the area of the sector are proportional to each other. And so then I actually have a situation where I know both measures of the angle and the angle and the area. By the way, this is an equivalent version of this is the part over known proportionality relation. If you happen to know the angle measure and the area at the same time at any point, then you could use that to create a proportion. So what is the part over whole? Again, or part over known. Known means that the two variables, in this case the angle measure and the area, are known simultaneously. Okay, so if we put this into the problem, the part of this circle is the area, so that's 7.5 pi is the part of the circle area, divided by the whole area. That's pi times 5 squared, which is 75. I'm sorry, 25 pi. I did a quick estimate, sorry about the 75. It's 25 pi. And that's equal to the part of the circle angle measure, that's equal to the measure of angle L, which is a mystery number, divided by the whole circle angle measure, which is 360 degrees. And notice that the only thing that's unknown here is the measure of angle L. So I'm going to cross multiply. Let's make that a 25 for the purposes of simplifying the cross multiplication. 25 pi in the denominator. So we got 25 pi times the measure of angle L is equal to 7.5 pi times 360. Now I'm actually, before I even multiply, I'm going to divide by the 25 pi in case things get ugly, because then I'd get a decimal, and I don't want to get the decimal if it's not necessary. Divide by 25 pi, and so that I get the measure of angle L equals, let's see, so there's some simplification that we could do. The pi's cancel. Okay, there is more simplification that we could do, but there's gonna come a point where I'm going to want to put it in the calculator anyway, so I might as well put it in the calculator now. But what I could do is I could 360 divisible by 5. I could divide by the 5. 7.5 technically is not, it's a decimal, so it's not evenly divisible by anything, but I can divide by 5 pretty easily. I get 1.5. So I can do it, but I'm going to not do it. 7.5 times 360 divided by 25. And I get 108. Let's minimize this, and we get that 108 degrees. And so we got the answer. That's it, 108 degrees. We circle that. And look at that. That is an angle between 90 and 120. And in fact, I said that it's between 90 and 120 if we assume that it's drawn to scale. Notice, once again, a problem that they didn't have to draw it to scale, but they did. So, by the way, problem 30 did secure us an 80 on this Regents. So we officially have an 80 on this Regents. We got 5 more problems to go. Congratulations on that. Number 31, using a compass and straight edge, construct the image of point A after a reflection over BC. Leave all construction marks. Now, this is one that I always do electronically for the purpose of showing how to do the problem. But when I teach this, I actually teach this fully electronically. The last thing that I do is put a compass in a kid's hand. Because if you look at the solutions, let's look at the solutions real quick. The solutions that are valid are given often using just dashes that look like dashes all over the place, or parts of arcs, and you're like, what do these things actually represent? And some of them are correct, some of them are incorrect. But the thing is, like, when students look at these diagrams, they look at dashes and they're like, I don't know what that means. And that's the thing. It becomes like, if you just draw parts of circles, it just becomes a weird thing that you have to memorize. Whereas if you actually learn it as drawing the full circle, you actually get it right. So when I teach this to kids, I actually ask them to draw the full circle every time. And here's the thing, it doesn't make it harder, it makes it easier. It actually just strictly makes it easier. So we have to do the reflection over BC. So we have to find a point. The point is, so this is not the actual construction. We have to find a point that's the reflection over BC. Well, there's something, this is not actually the most accurate location. Why did it, there we go. It's more like here, but we'll call it A prime. But what's true about that point? Well, if you draw this line segment, that's a little too far. Okay, I'm gonna erase this A prime and put it over here. If you draw that there, that is a right angle. What else is true though is that A and A prime are equidistant from B. Okay, it didn't make that one nice and straight, but and C, A and A prime are also equidistant from C. I don't know why it's not making those straight. Okay, but fine. So these are equidistant as well. And of course, these are equidistant. So what kind of a shape is that? It's a kite. But how can I know that I have a line segment from B to going to A and A prime that are congruent? Well, what I happen to know is that if there is a circle centered at B, then that goes through A, it's going to also go through A prime. And why? Because a circle has a constant radius. Similarly, if I know I have a circle centered at C going through A, it's going to also go through A prime. Why? Because the radius of a circle is constant. So in fact, that's what I'm going to use to construct it. So I go back to this. I'm going to draw a circle from B through A. Now, wherever A prime is, it's going to be somewhere over here. I don't know where it is, but it is on this circle because A and A prime, BA and BA prime are congruent to each other. Okay, that's the reason. Similarly, and let me move this one down a little bit. So it was actually lower. Okay, good. Similarly, CA and CA prime are congruent. So if I have a circle from C centered at C through A, then CA is congruent to CA prime because they both have to be radii of the same circle. The intersection of those two circles has to be the location of A prime. So we've constructed the reflected point, and there it is. So that's the full theorem. All that this is a circle centered at B. So you would put the needle at B, and you would put your pencil at A, and you would draw a full circle. Forget about drawing just part of an arc. That's confusing. Guessing at where the locations are. No, draw the full circle. Just draw the full circle. Then you put the needle at C, and you put the pencil at A, and then you draw a full circle. And the intersection of those two circles is A prime. Well, one of the intersection of those two circles is A. The other intersection of the two circles is A prime. So we've gotten the location of A prime. And that's 2 points. So this, let me just make sure that we're not confusing you here. This is just expository explanation. This is not a construction because I kind of had to guess at the location of A prime. That's not a construction. Again, this is a construction. Circle centered at B through A, circle centered at C through A. Draw the intersection of the two circles. And we just got a perfect part 2. Congratulations. And now, and by the way, we haven't even found a single diagram that's not truly drawn to scale, or other than the degrees of freedom that still exist within that shape. So why is it that the diagrams need not be drawn to scale? So the one important thing to understand, the true definition of drawn to scale is that all angles are the same size, and also all lengths are the size that they appear to be. And sometimes a diagram has degrees of freedom that allow lengths to change. However, if the parts that are measured are drawn to scale, then the other parts that are not measured don't necessarily matter. And in most situations, they just don't matter. So like when they tell you what's the measure of a certain angle, and all the parts that were measured were drawn to scale, then the angle measure has to look like the measure that it actually is. Similarly, if everything that they drew is drawn to scale, and as labeled, and then they ask for a length, then that length, assuming that it's well defined, has to be drawn to scale. So that's the thing. So that's why we can cross out the words not necessarily and put almost definitely. And that gets us points in the guessing process. Number 32, Joan wants to fill an empty 75-liter fish tank with water. She uses a cylindrical bucket with a diameter of 20 centimeters. Determine and state the maximum number of buckets of water filled to an exact height of 26 centimeters Joan can put into the fish tank before it overflows. Before it overflows. Okay, so it looks like we need the volume of the fish tank, and then we need the volume of the bucket. They actually told us the volume of the fish tank. Now this, and they told us the scale between centimeter cubed and liters. 1,000 centimeter cubed is 1,000 milliliters, which is 1 liter. But we don't need the 1,000 milliliters. I'm just stating that for the nerds. So we know the volume of the fish tank. So let's actually calculate then the volume of the bucket. We know that the bucket is a cylinder of height 26, exactly 26 centimeters, and a diameter of 20 centimeters. This is not a trick question. They're giving you the diameter. You need the radius to get the volume. R equals 10 centimeters. So the radius is equal to 10 centimeters. And that's the worst 10 ever. 10 centimeters. And the height is equal to 26 centimeters. And so then what's the volume? Volume is equal to, again, base times height according to the formula sheet on the Regents. This is the volume of a general cone, right? Or a general cylinder, I believe is what they said. Cylinder. B is the area of the base, where B is equal to the area of the base. of base. Oh, that's terrible. The area of the base, which is equal to pi r squared, which is equal to 100 pi. Okay, so the volume is equal to 100 pi times the height 26, which is equal to 2600 pi. And then this is in centimeter cubed. And if 1,000 centimeter cubed, if 1 liter is 1,000 centimeter cubed, 1,000 centimeter cubed, then that's equal to some mystery number of liters divided by 2,600 pi centimeter cubed. And I could cross multiply, and I got 1,000 VL, V in liters. That's equal to 2,600 pi times 1 divided by 1,000, and I got that V is equal, V in liters is equal to, well, 2.6 pi liters. I should say, yeah, and this is equal to the volume of the bucket. So this V, I'm going to change the L to a B for bucket. Notice that the volume of the bucket is 2,600 pi centimeter cubed, but it's also 2.6 pi liters. And so then how do I get how many buckets it takes to fill the 75 liter fish tank without overflowing? So then it's V of the tank divided by V of the bucket. And that's equal to 75 over 2.6 pi, which is approximately, now the calculator is going to tell me, and a decimal answer. Let's see, 75 divided by, parentheses, 2.6 pi. Another error that's common for students, rearing its head. A lot of students just don't put the parentheses in the denominator, but they are required. And they get around 9.182015948, and this is approximately equal to, let me scroll up a little bit. So just let's remember what they said. They want to know the maximum number of buckets of water filled to exact height of 26 centimeters that Joan can put in the fish tank before it overflows. So if she could put 9.18 and it gets to the exact tippy top of the tank, putting 10 would be too much. It would overflow by a lot, and that would be a big mess. Or she could put 9, and that's the maximum that she could put. So the max number of buckets is equal to 9. Number 33, as modeled in the diagram below, 2 cables are attached from a point on a tree 12 feet above the ground. The longer cable is anchored to the ground 3 feet farther from the tree than the shorter cable. Okay, is anchored, and the angle of elevation between the shorter cable and the ground is 50 degrees. Determine and state to the nearest foot the distance from the base of the tree to where the longer cable is attached to the ground, and also this is a part 3, so it's a 4-point problem, 2 parts. Determine and state to the nearest degree the angle of elevation between the longer cable and the ground. Just to be clear, suppose you make a mistake on the first part of the problem, but you use that in the second part, they don't penalize you for getting the first part wrong again in the second part. So just get something for the first part, and if you need to use it for the second part, it's actually a valid answer still. Okay, so let's talk about scale real quick, because this is a nice way to just eke out a point or two if you're lucky. On the part ones, you can eke out a point, or you can eke out 2 points by using scale to get the answer exactly. On the part 2s, 3s, and 4s, you need to just estimate as best as you can. And look at this. The height of the tree is 12. can't violate that with just one number. So the second number they gave us is the length 3 down here. Does the 3 look like a quarter of the length 12? Actually, yeah, 3 and 3. So that 3 and the 12 are drawn to scale. That 50-degree angle, does that look like a little bit more than 45? The equivalent question, does that angle look like a little bit less than 45? Yes. So that angle's drawn to scale. This diagram's drawn to scale. So the first part of the problem says to the nearest foot, the distance from the base of the tree to the point where the longer cable is attached to the ground. If I guess that length, so I'm going to call this point B. I'm going to call that point A. I'm going to call this A prime. Okay? If they want to know the length where the longer cable is attached to the ground. If I guess at the length of A prime, and I happen to guess correctly, I get a point. And they said to the nearest foot. They could have made it meaner and said to the nearest tenth of the foot so you couldn't guess. But by making it an integer, and I noticed that BA prime is almost the same length as BA, as B to, call that C, 12. But just looks a little bit longer. So if I just guess an integer slightly bigger than 12, I might get so lucky. And it's now I got a 50-50 chance. If I guess 13 or 14, I got a 50-50 chance. In fact, if I guess 13, which is what I would have guessed, that's a point. Because if you just state the number and you don't get it, and you don't have any correct work to get it right, that's a point. Where does it say that? It says it. Let's see if it says it in the this part. A correct numerical answer with no work shown will receive only 1 credit. So they give a point. So you do have to guess the 13, and you have to guess the angle, which again, I'm going to talk about how to come close to guessing that soon too. So, but there's a big chance that if you just guessed the numbers right, you'd get a point. Worth a shot. So get your points. Now, how do I actually get BA prime? I don't have enough information on the outside triangle because I don't have 2 parts of the triangle. I'm sorry, I don't have 3 parts of the triangle, so the triangle is not yet uniquely determined. However, this problem does have 3 degrees of freedom: the location of A, the location of A prime, and the location of C, given that this is a right angle. So it has 3 degrees of freedom, and I have 3 pieces of information: the 12-foot height, BC, the angle, BAC, 50 degrees, and the length of AA prime, which is 3. 3 algebraically independent pieces of information, 3 degrees of freedom eliminated. I can get the answers to these problems. So the question is not how do I get A prime in 1 step, because you should not assume that I can get BA prime in 1 step. It might take 2 or 3. So, and that's actually the way geometry ends up working. In fact, almost always it's the case that you have to do multiple steps to get one number. In other words, you have to use different parts of geometry lessons from across the year to get one thing. The inner triangle CBA, does have 3 pieces of information determined: the height 12 BC, the angle 50 degrees, angle BAC, and the right angle at on the bottom left. So I can get BA. How do I get BA? Well, BA is the leg adjacent. BA is equal to the leg adjacent to the 50-degree angle. And then BC, which is equal to 12, is equal to the leg opposite the 50-degree angle. And I also have SOHCAHTOA. And we got to use all 3 of these. The only one that has the leg opposite and the leg adjacent is the tangent. So tan of that angle, angle BAC, is equal to the leg opposite divided by the leg adjacent. And so I put the numbers in. I got tan of BAC, tan of 50, is equal to the length of the leg opposite, 12. This is BC, and this is the leg adjacent, BA. 12 over BA. It's okay that I don't know BA, because if I did know BA, I would just state the length of BA, and I'd be on the second part of the problem. This equation only has 1 unknown, so I'm going to put the tan 50 over 1, do the cross multiplication that I know you kids love to do. and I got 12 times 1 is equal to BA times tan 50. And I divide by tan 50, divide by tan 50, and I get that BA is equal to 12 over tan 50. And this is where I get my calculator out. Let me bring that over here so you could see my calculator. So 12 over tan 50, 12 over tan 50, and that's equal to, it's approximately equal to 10.06919557. And you know my rule, I put all the decimals and then round later. They didn't ask me for BA, so I can't round quite yet. They want the length from the base of the tree to the longer cable, so they want BA prime. So BA prime, which is equal to BA plus AA prime, is equal to, well, this 10.06919557 plus 3, which is equal to 13.06919557, which is rounded to the nearest. Now I look to the nearest foot, 13. And they gave me the units, so I do not have to give the units. And in fact, it might be better that I don't. 13. And like I said, if you had guessed 13 or 14, you'd have a 50-50 chance of getting that part. Now, unfortunately, you do have to guess the second part numerically also to get the 1 point from guessing. But this is the angle that they're asking for. Determine in state to the nearest degree the angle of elevation between the longer cable and the ground. But again, this is a 50-degree angle. If I guess something very, as an integer, somewhat close to 50 degrees, but remember, 50 degrees is a big number, so close is anywhere between 40 and 50. Less than 50, right? If I just got lucky and guessed a number between 40 and 50, and it's probably not 40, because this angle's 40, then I might get lucky. Let's find out what the actual measure of angle A prime is. So now I know this length is 10 and this length is 13, right? I know those lengths. Now I do have 3 parts of triangle BCA prime determined. The height, 12, the base, 13, and then the angle A. So again, for the outside triangle, BC is equal to the leg opposite angle angle A prime. And then the bottom side is the leg adjacent. So BA prime is equal to the leg adjacent to angle A prime. Angle A prime, rather. And so I use SOHCAHTOA again. With the one that has the leg opposite and leg adjacent. So I got tan A prime is equal to the leg opposite, which is 12, over the leg adjacent. Perfectly valid question. Do you use the 13 or do you use the 13.06919557? You are allowed to use the answer from the previous question, so you are allowed to use the 13. Okay? So that's equal to, well, 12 over 13. Now there's another part of the tangent that you have to remember, the inverse function. How do you undo tangent? How do you undo tangent? Well, tangent is a function. So the way you do the the way you do the inverse of a function is you literally have to use the inverse of that function on both sides of the equal sign. So if you undo the tangent, you're left with A prime, and on the right side, you're left with the tan inverse of 12 over 13. And so A prime is approximately what the calculator is about to tell us, and we're going to use the decimals again. Tan inverse is right above the tangent button in blue, so we press the blue second button, and we press tan inverse, and 12 over 13. we know that that angle, a little bit more estimating. I said an angle between 40 and 50, right? And then you get the answer right. There's another piece of information that you know. The base, BA prime, is bigger than the altitude, BC, which means that that angle A prime is opposite the shorter leg, which means that A prime is going to be the smaller angle between angle A prime and angle BCA prime. So angle A prime actually has to measure not less than 50, it has to measure less than 45. So if you guess a number between 40 and 45, an integer between 40 and 45, now you have a much bigger chance of getting it right, worth guessing. Halfway between 42 or 43, you got a 50 chance of getting it right. If you do guess between those, 41, 42, 43, 44, right? You got a 1 in 4 chance of getting it right. Or if you guess between 42 and 43, it turns out to be 50-50. 12 over 13, 10 inverse 12 over 13 is 42. 42.7093896. I put all the digits and then I circle what they said to round to the nearest degree. A prime, the measure of angle A prime. If you don't put measure of angle A prime, if you just say prime, A prime, they actually accept that. The measure of angle A prime is approximately around this up now to 43 degrees. And that's a point. Number 34. Quadrilateral read, R-E-A-D, has vertices with coordinates R, -1, 3, E, 2, 7, A, 10, 1, and D, 7, -3. Prove that read, quadrilateral read, is a rectangle. The use of the axes is optional. There's probably there's not a second part to this, which is great. How do we use the they said it's optional, but I use them. -1, 3, -1, 3, 2, 7. Now notice that I'm just putting down the points. I 100% guarantee you though, I am counting. I just happen to be really good at graphing points. 10, 1. I just visually know where those are. You probably don't. So you should be doing 7, -3, D, 1, 2, 3, 4, 5, 6, 7, -1, -2, -3. So that's 7, -3, -1, -2, -3. That's what you should be doing. Don't assume that just because I drew it so fast that I didn't actually do the work. So R, E, A, D. We have to prove that this quadrilateral is a rectangle. And it does look like a rectangle, doesn't it? There you go. Come on, make it straight. Nope. Why? There we go. Why is it taking so long? Okay. So it does look like a rectangle. And so there are a lot of statements that are true about rectangles. So like a rectangle is a parallelogram with a right angle. So if you prove that it's a parallelogram with a right angle, then you've proved that it's a rectangle. Or if you say it's a parallelogram with one pair of perpendicular sides, then you've proved that it's a rectangle. If you prove that the opposite sides are congruent and it's got a right angle, then it's a rectangle. So the way I'm going to go about it, because I know how to calculate the slopes pretty easily, I'm going to do this by the slopes. Because the slopes will prove simultaneously that opposite sides are parallel, and because perpendicular sides have slopes that are opposite reciprocals of each other, it's going to simultaneously also prove that one pair of sides is perpendicular. So so a rectangle is equal to a parallelogram So it's got two pairs of parallel sides with a pair of perpendicular sides. So I'm going to get the slopes. And then RE. So remember slope. The slope is equal to change in y over change in x. So the slope of RE is equal to the change in y. So I subtract the two y coordinates, e minus r. I go 7 minus 3 over the change in x, subtracting the x coordinates, e minus r. So 2 minus 1, 2 minus negative 1. That's not a line. 2 minus negative 1, which is equal to 4 over plus 3. Okay? The slope of EA is equal to, again, change in y over change in x. I'm going to do a minus e in that order. So 1 minus 7 over 10 minus 2, which is equal to negative 6 over 8, which is equal to negative 6/8, which is equal to negative 3/4. So notice already that RE is perpendicular to EA because the slopes are opposite reciprocals. Of each other. So I've already confirmed that it has a pair of perpendicular sides. Now I just got to prove that it's a parallelogram. The slope of AD is equal to, again, change in y over change in x. I'm going to do d minus a because that's the way I wrote it, final minus initial. The change in y is negative 3 minus 1 over change in x is 7 minus 10, which is equal to negative 4 over negative 3, which is equal to 4 over 3. And as a last one, I'm going to show you that the calculator can simplify fractions. The slope in two ways. So I'm going to show you a way that's really very nice and useful for kids who really struggle remembering parentheses, although you should just not forget parentheses. A lot of students are, believe it or not, actually truly lazy with parentheses. They purposely don't put parentheses because they're trying to purposely find the simplest way to do the problem, when in fact they don't realize that all the work that teachers are doing, they're literally showing you the simplest way to do the problem. They're not actually showing you a more complicated way. They're actually showing you the simpler way. Anyway, the slope of dA is equal to, I'm going to do a minus d because that I wrote it in order dA, final minus initial. The final is a, the initial is d. So a, let's see. I'm sorry, I did dA. I need to do, dA is AD. I need to do dr. dr is equal to final minus initial, so r first, 3 minus negative 3 divided by negative 1 minus 7. And I better get 3/4 out of this. But this one I promised you that I would show you on the calculator, so I'm going to show you this one on the calculator. So I get, so there's a couple of ways to do it on the calculator. If you put parentheses, it'll do it. But there's another way. If you go to math and put number, the last option is n over d. That's how you can put an actual proper fraction with a horizontal fraction bar on the calculator. Now, if you didn't know that, and now you know that, hit the like button. Again, if you click math, go 1 to number, and go to the last option, n over d, that puts a horizontal fraction bar on your calculator. So horizontal fraction bars do appear on the calculator. If you do 3 minus a negative 3 in the numerator And then in the denominator, you do -1 minus 7. Oops. There we go. -1. I pressed. Okay. If you press the down arrow, it goes to the denominator. -7. It's going to give this answer as a simplified fraction, and I get -3/4. Simplified fraction. It's nice. So I have that it already has a pair of of perpendicular sides because they have opposite reciprocal slopes. Now I have to show that they have two pairs of parallel sides. Notice that RE and AD are the slopes of RE and AD are equal. So RE is parallel to AD because the slope of RE is equal to the slope of AD. And we also have that the slope, that EA is parallel to DR because the slope of EA is equal to the slope of DR. So we have two parallel sides, two pairs of parallel sides. So READ has two pairs of parallel sides. So it is a parallelogram with a pair of perpendicular sides. So it is a rectangle. There we go. We've proved that it's a rectangle and we've gained 4 points. And we are about to ace this test. I would just want to do a quick view of the grading of this. So we got to an 80 after we got 60 points. So where did we have 60 points? That was at 30. Problem 30 secured us an 80 on the Regents. But which one gave us a 90? A 90 on the Regents was gotten when we had 72 points. Notice that this test is out of 80 points. The last problem is 6 points. So the whole test minus the last problem is 74 points. So we actually secured a 90 in the middle of question 32. Halfway to question 34. Halfway to question, I just read 32 on the screen. Halfway to question 34 is when we secured the 90. It takes a lot of work to secure a 90. Now, does that mean that we have to get that many problems perfectly right to get a 90? Actually, no, because most of the time, if you're actually aiming for that 90, you don't have to get all of those points and then get 0 points at number 35. You actually work to lose no more than a point here and there, and you maximize your grade. You should, of course, aim to get every question right. But if you show work on every single question, including the part 1s, and 2s, 3s, and 4s, including the part 1s, though, even though they don't look at your work on the part 1s, if you show work on the part 1s, you're going to maximize your grade. So now, on this problem, we are going to cross out the words not necessarily drawn to scale. Where is it? Not necessarily. Once again, cross it out again and put almost definitely. Number 35. I hope you're excited. We are about to ace this Regents. This is super exciting for me. I hope you've appreciated what's been on this video. If you do, please do hit the like and subscribe button. And if you need my videos for the next Regents, please do watch my videos. I do some of the science videos. I haven't been doing the bio and earth science, but I think I'm going to hop back to those really soon. So I would do maybe 7 videos per year, but I do all the math videos, Algebra 1, Geometry, and Algebra 2, and I do the chem and the physics as well. So definitely keep watching. and watch for the next video as well. If you do appreciate this video and you feel like it helped you, please do mention it in the comments, because I thrive on knowing that I've helped you pass this Regents. So number 35, in quadrilateral ABCD below, side CD is extended to point E such that AFD and BFE bisect each other. It sure looks like they bisect each other. And DE is congruent to DC. Prove that ABCD is a parallelogram. So I put the statement and the reason here, and the reason here is given because I hope you know you have to start that way. You have to give all the given information at least at some point. I used to recommend to students to give the given information only when you actually use it. But I don't do that anymore. Just write the given information whenever you have it. That said, it does look like a parallelogram, and I have to remember how to prove a parallelogram or a quadrilateral is a parallelogram. Parallelogram has, if I could prove that it has two pairs of congruent sides, great. If it has, by definition, two pairs of parallel sides, great. I've proved it's a parallelogram. If I proved one pair of sides is both parallel and congruent, then I've proved that it's a parallelogram. If I've proved that both pairs of opposite angles are congruent, then it's a parallelogram. And finally, if the diagonals bisect each other, then it's a parallelogram. I don't have the diagonals, so I'm not going to prove that they bisect each other. I really don't have anything to attack angle C, so I can't prove that opposite angles are congruent right now. So it's either one pair of opposite sides, both parallel and congruent, or two pairs of sides parallel and two pairs of sides congruent. Another one, I don't have a way to attack angle C, so I probably can't prove that BC is parallel to AD. So I'm not gonna attack angle C. So I'm actually gonna try to prove that one pair of sides is both parallel and congruent. That's my intuition. But if you didn't know enough to make that assessment, what you should do is start proving things, because this is a 6-point problem. If you do correct things, it's almost exactly a true statement to state that every true statement beyond the givens is a point. Every correct statement that you've proved is a point. That's almost a true statement. It's not quite true because some proofs take more than 6 steps, but it is very close to true. And in fact, so I'm going to start. Remember, they already told us that DE and DC are congruent. But these other ones that I labeled with 1 dash, they didn't say that they're congruent. They said that the two line segments bisect each other. So I have to say that they're congruent. And so that's what I'm going to do. I'm going to switch to, let's say, black. Okay. So statement 2, I'm going to state that the two pairs of the sides that are cut are going to be congruent. So I'm going to say that EF is congruent to BF. EF is congruent to BF because the bisector cuts, but this is the definition of a bisector, cuts a segment into two congruent segments. And in fact, statement 3 is the same. So I state that FE and BF are, and FE are, FE and FB are congruent, but also FA and FD are congruent. I don't like the way I stated this. No, this is fine. EF and BF. This is fine. The vertices have to be given in order. I'm going to say that DF is congruent to AF for the same reason. That a bisector, can you do like quotation marks? Yeah, you can. But I'm going to, I don't want you to skip steps, so I'm going to write it. The bisector cuts a segment into two congruent segments. So I've gotten 2 statements. That, depending on the grader, that may be 1 point or 2 points. But notice all I've done is write things that I can prove. Write things that I can prove. So I am going to go back here, make another column here. Statement and reason. And now I have, in those 2 triangles on top and on bottom, I have 2 pairs of sides congruent. Now, let's see. I have this pair of angles congruent because vertical angles are congruent. So I have that, this is statement 4. Now I go back to my black. 4. That angle AFB is congruent to angle DFE because vertical angles are congruent. And why did I want to use that? Because now I have 2 pairs of sides and the included angle, so I know that these 2 triangles are congruent by side angle side. So statement 5 is that triangle AFB is congruent to triangle, let's see, AFB DFE, triangle DFE, and because by the side angle side postulate. Some teachers write side angle side, or I like side angle side congruent to side angle side, or you could just write SAS. Okay. SAS is enough. So now I have those 2 triangles congruent, which makes all corresponding parts of the triangles congruent, which means I could put 3 dashes up here because AB corresponds to DE. So, and DE has 3 dashes on it. They're congruent to each other by CPCTC. So AB is congruent to DE by CPCTC. Okay? CPCTC is corresponding parts of congruent triangles are congruent. And that, by the way, I haven't said that AB is congruent to DC, but they are now because they both have 3 dashes. But the reason is that by the transitive property. So 7, DC is congruent to AB by the transitive property. So now I have the top and bottom sides of this quadrilateral are congruent. Now I have to prove that they're parallel. How do I prove that they're parallel? I'm going to use AD as a transversal. I could use AD as a transversal, or I can use BE as a transversal. Which one do I use as a transversal? Yeah, I like, I'm going to use AD as a transversal, but the same exact proof is true if you use BE as a transversal for parallel for the 2 line segments on top and on bottom. So I'm going to say this angle with a dash is congruent to this angle on top with a dash. But I don't have parallel sides, so I can't use like alternate interior angles. I have to use the corresponding parts of congruent triangles. So 8 is that angle EDA, EDF is congruent to angle BAF for the same reason as before. Its corresponding parts of congruent triangles are congruent. So 8, CPCTC. And now that I have that those 2 angles are congruent, then the top and the bottom are parallel. So EDC EDC is parallel to AB because if you have 2 segments with alternate interior angles congruent, then they are parallel. There you go. So segments with congruent alternate interior angles are parallel. Segments with congruent alternate interior angles are parallel. And so that makes the sides A, B, and DC parallel. So statement 10 is that AB is parallel to DC because, well, parts of parallel lines are parallel. Parts of parallel lines are parallel. And now we're about to finish and get a full 100 on this region. So we got two more statements. We got that the top and the bottom are parallel. So 11 is that AB, and we're about to drop the mic. So AB is, so that it's not two more steps, sorry, it's one more steps. It's one more step. Step 11 is that ABCD is a parallelogram because we're about to drop the mic. So let's do this. Ready? So a quadrilateral with, this is a long proof, with one pair of sides, both parallel and congruent, is a, and this is the end symbol, parallelogram. And at that point, we pick up the mic, we drop the mic, and we are done. We got 100 on this test. Congratulations, and I will see you in the next video. Good luck on your Regents.